Let's look at another example, related example. So example 2, if we have a two-sided exponential, what will happen? So xt equals exponential minus a, and then absolute value around the time, which can be written as this when t is positive. When t is positive, let me write it separately here. So the absolute value of t is, when t is positive, we get t. When t is negative, we get minus t. So this is when t is positive. It's when t is less than 0. So this can be written as exponential minus at and exponential plus at. Minus at when t is positive, and we get exponential at when t is negative. Now we'll do similar, we'll follow similar procedure to find the Fourier transform xj omega of this signal by doing this integral minus infinity to plus infinity xt exponential minus j omega t dt. Now our signal is defined piecewise. One piece is defined when t is positive, the other is when t is negative. So we'll split this integral into two integrals, each one for each piece of the signal. So from 0 to infinity, we have the first part of the signal, which is exponential minus at, exponential minus j omega t dt, plus from minus infinity to 0, we have the second part of the signal is exponential at, exponential minus j omega t dt. And this will be, if we combine those two exponentials, plus infinity, we'll have exponential minus a plus j omega times t dt, plus integral minus infinity to 0 exponential, let's keep it like that. So a minus j omega t dt, and this will be 1 divided by minus a plus j omega exponential minus a plus j omega t from 0 to infinity. And then this part is 1 divided by a minus j omega exponential a minus j omega t from minus infinity to 0. And plus infinity. So when t goes to plus infinity, we will have exponential to minus infinity, and this will go to 0 when t goes to plus infinity. So we'll have 0 minus exponential 0 is 1, so minus 1 divided by minus a plus j omega plus plus when we have 0 here, so we'll get 1 divided by a minus j omega minus when t goes to minus infinity, this goes to 0. Assuming that this term is positive. So this goes to 0, and then we have 0 here. So the final Fourier transform of this signal is 1 divided by A plus J omega plus 1 divided by A minus J omega. And we can rewrite this by multiplying this term by A minus J omega and this term by A plus J omega. So you get A minus J omega plus A plus J omega divided by A square plus omega square. And then those terms cancel. And we get 2A divided by A square plus omega square. Notice that here the Fourier transform of this signal is real. And also it's even in terms of omega, because we have omega square, so x j omega equals x minus j omega. The function is even because of this omega square. So it's real and even. And if we look at the signal itself, the signal itself, xt equals exponential minus a absolute value of t. If we want to plot this signal, first of all, it's real. But if we want to check if it's even or odd, let's have a look at if we plot it, when t is positive, we have a decaying exponential. So from 1 and exponentially decaying. And when t is negative or less than 0, we have exponentially growing from minus infinity till 1. And if you look at this signal, this is an even signal. So when the signal is even and real, we get a real and even Fourier transform of the signal. And if we want to plot this one, it will look similar to this from the previous example, but the scaling will be different, but the shape will be the same. And again, this one will be also a low-pass filter, similar to a low-pass filter. And also, this is real. Real, then if you want to find the magnitude, it's the same as the xj omega itself, because it's real.